we begin with the definition. Let F be an ordered field. Define the absolute value function. Denoted modulus from F to F. Note that I have put a bold dot. That's supposed to denote where the function is plugged in. This is sort of a weird notation for a function, but it is commonly used in mathematics. The definition is mod x is defined to be equal to x if x is greater than or equal to 0 minus x otherwise. So this definition is no doubt familiar to you from your studies before. The absolute value in the rational numbers Q has a nice geometric interpretation as the distance from the origin. This absolute value will always give you a non-negative element. It is designed in such a way that if it is positive, it returns back the same number. If it's negative, it returns the negative. So you will get always a positive answer to this. So we will require only the basic properties of the absolute value. One big inequality we will require later in series. It's better to do it right then and there. So let's state a theorem, or rather a proposition. It's not such an important thing to call a theorem. Proposition. Let F be an ordered field. Then we have various properties. For each x in F, we have mod x greater than or equal to 0. Moreover, mod x equal to 0 if and only if x is equal to 0. Number 2, for all xy in F, modulus of xy is equal to mod x multiplied by mod y. Number 3, this is the most important, subadditivity or triangle inequality. So the name triangle inequality comes from the fact that the sum of two sides of a triangle is at least as large as the third side. One needs to go to several variables to exactly see why this is called a triangle inequality. We will see that in the section on topology. For all xy in F, modulus of x plus or minus y is less than or equal to mod x plus mod y. Okay, so this is actually two inequalities that I have condensed into one inequality by using the plus or minus sign. Fourth is called the reverse triangle inequality. The reverse triangle inequality says the following. It says mod x plus or minus y is greater than or equal to mod x minus mod y. Why it's called the reverse triangle inequality is easy to see. In fact, I can put a modulus sign here on the right hand side as well. Okay. 5. For all x, y, z in the field, mod x minus y is less than or equal to mod x minus z plus mod y minus z. Okay. So it's a simple list of properties. Almost all the properties can be given very simple proofs. Let's see the proof of this. First is the obvious thing that mod x is always greater than or equal to 0. This is obvious, but nevertheless, let me write down a proof. If x is greater than or equal to 0, then mod x is equal to x, which is greater than or equal to 0. Okay. If x is less than 0, then mod x, which is equal to minus x, is also greater than 0. Okay. Where the fact that if x is less than 0, minus x is greater than 0 follows from the fact that the negative of a negative element is positive. It's one of the properties of an ordered field. Now let me make a remark here. Here the proof is what is known as a proof by cases. We want to prove something, more precisely we want to prove that mod x is greater than or equal to 0, irrespective of what x is. What we do is we split into two cases. The first case is when x is greater than or equal to 0. The second case is when x is less than 0. Then we proceed and give an independent proof for both cases. This will prove that whatever we are trying to assert is indeed true for all elements x coming from the field F. So proof by cases is probably one of the most common techniques used in a proof, especially in really long proofs, where you will not just have two cases, you will have several dozen or even several thousands in some of the deeper theorems. Okay. Now, let's try to prove the rest. First, let's make an observation. Notice that mod x is always plus or minus x, depending on the sign of x, depending on whether x is positive or negative. So the modulus or the absolute value is always going to be the same as what you are going to put as an input, except possibly the sign could change. Well, that immediately gives, therefore, modulus of xy is certainly going to be modulus of plus or minus 1 times mod x times mod y. How did I get this? Well, it's got to be mod xy has to be plus or minus xy. Okay? And we already know that x is going to be plus or minus mod x. I'm just reversing the role. Mod x is plus or minus x, therefore x has to be plus or minus mod x. Similarly, y has to be plus or minus mod y. Okay? The net upshot of all this is mod xy has to be plus or minus of mod x mod y, and we know that this sign also you need to put a modulus there simply because mod xy will always be non-negative. So technically I can get rid of this plus or minus mod 1. Okay, modulus of plus or minus 1 can be immediately gotten rid of. So it immediately follows that mod xy is equal to mod x times mod y. Okay, now let's deal with the subadditivity or triangle inequality. Well, from all these remarks, it should be clear to you that mod x is going to be greater than or equal to plus or minus x, always. Okay? Why does this follow? This follows because observe that mod x minus x will always be greater than or equal to 0. Check why this is true. So mod x is always greater than or equal to plus or minus x. Similarly, mod y is always greater than or equal to plus or minus y. Okay. Now, we immediately get by one of the properties of an ordered field that mod x plus mod y is greater than or equal to plus or minus x plus or minus y. Fine. Actually, to be 100% precise, this is a bit confusing. I'll just write plus or minus x plus or minus y. Okay. Now, I am being very sloppy in the notation because the proofs here are quite easy, but I shouldn't be too loose so as to confuse you. First, notice that when I wrote mod xy is plus or minus xy here, or mod x is plus or minus x, I do not mean both possibilities. I do not mean both possibilities. I just mean that mod x is going to be either plus x or minus x depending on the sign of x. Ditto for mod xy equal to plus or minus xy. But here I am being a bit loose to simplify on the amount of writing. For brevity's sake, I am writing mod x plus mod y is greater than or equal to plus or minus x plus or minus y. Here I mean irrespective of what combination of the plus or minus signs you have for x and y, this inequality is still true. So in these three places, or rather 4 places, you should take it as any of these signs are allowed. Any of these signs are allowed. Okay. In the previous cases, only one of them, the equality is true for only one of them. Mod xy is either equal to xy or it's equal to minus xy. It's not equal to both. Okay. Now you have mod x plus mod y greater than or equal to plus or minus x plus or minus y, where all possibilities are allowed. There are 4 possibilities. There are 4 possibilities for the right hand side. Now observe that these quantities mod x plus or minus y, we want to show that mod x plus mod y is greater than or equal to mod x plus mod y, mod of x plus y, and mod x plus mod y is greater than mod x minus mod y. Observe that these quantities mod x plus y and mod x minus y, these are 2 of the 4 possibilities here. 2 of the 4 possibilities. Okay. So check that 2 of the 4 possibilities here are indeed going to be modulus of x plus y and modulus of x minus y. That means we immediately get both. We immediately get mod x plus y is greater than or equal to mod x plus mod y, and mod x plus y is greater than or equal to mod x minus mod y. We get both. Okay. So that completes the proof of subadditivity or triangle inequality. Now how do you prove the reverse triangle inequality? That's not too hard either. We want to show, let me just show one part. Let me just show you that mod of x plus y is, or rather let me show the minus sign. That looks like a bit harder. Mod of x minus y is greater than or equal to modulus of mod x minus mod y. Okay. Now how do you show this? Well, look at mod x plus mod y minus x. Sorry, modulus of x plus y minus x, not mod x plus mod y minus x. This is by the triangle inequality less than mod x plus mod y minus x. Okay. But this is nothing but modulus of y. Okay. So you immediately get mod of y minus x. Mod of y minus x is greater than or equal to mod y minus mod x. Okay. So we also get mod x minus y is, by the same argument, is greater than or equal to mod x minus mod y. But mod y minus x and mod x minus y are the same. Again, check. All things that are trivial, which can be checked in a line or two, I am leaving to you. So putting these two together, we get mod x minus y is greater than or equal to modulus of mod x minus mod y. Why do we get these? Because modulus of mod x minus mod y has to be one of these two. That's the reason. So that proves the reverse triangle inequality. Of course, I am leaving another case, but that is equally simple. Finally, we want to show that for all x, y, z, mod x minus y is less than or equal to mod x minus z plus mod y minus z. This immediately follows by writing mod x minus y has mod x minus z plus z minus y. And then this will immediately give mod x minus z plus mod y minus z by triangle inequality, and we are done. So this concludes the proof of these basic properties. Now let me give you an exercise. See which parts of the above result can be modified for n elements. We had only 2 elements, or at the max 3 elements. Think over which of these properties can be extended to many elements. Okay. Now I am going to end this section with a simple proposition which is so simple that I will never ever explicitly mention that this proposition is being used in the course. So let me write down this proposition and let me put a double star or a triple star next to the proposition. This is to indicate that this proposition has to be committed to your memory. If I wake you up in the middle of the night and ask you what is proposition about elements in an ordered field being arbitrarily close, you have to know it. So some amount of memorization is impossible without any, some amount of memorization is unavoidable in any subject of study, and this is one of them. Elements in an ordered field cannot be arbitrarily closed. Arbitrarily close. What this proposition says is rather simple. Let F be an ordered field. A comma B in F. Suppose for each epsilon greater than 0, we have modulus of A minus B less than epsilon, then A is equal to B. Okay? What is this proposition trying to say? It is saying that regardless of what value of epsilon you choose, epsilon being any positive element in the field, note this epsilon is coming from F. Let me be precise. Epsilon is coming from F. Irrespective of what epsilon you choose, positive coming from the field, if it so happens that modulus of A minus B is less than that, then A is forced to be equal to B. Why is this the case? Well, first, let me give a proof trip. We are going to apply a proof, but prove only one case. Remember when I made a comment about proof by cases, where we split the number of cases into 2 or 3 and prove each case independently. Here what we will do is we will say without loss of generality, assume A is less than B. What does this mean? Essentially, I am going to appeal to a proof by cases But if I prove the case A less than B, then there is no necessity for me to prove the case B less than A. Why is that? Because at the end of the day, A and B are just symbols. If I can show that when A is less than B, the result is true, obviously the same has got to be true when B is less than A, because the final result does not give any priority to the role of A or to the role of B. The way it is written, you have a feeling that A and B indeed have asymmetric roles, but that's not the case, because A minus B is same as B minus A. Modulus, of course. Modulus of A minus B is same as modulus of B minus A. So there is no distinguished role for A or B. So if I can prove the case A less than B, then I'm done for the case B less than A also. Okay. So I'm going to assume that A less than B and reach a contradiction. That means if I assume B less than A, I will also get a contradiction, which leaves the only possibility that A has got to be equal to B. Okay, so when in such situations, when you are making a proof by cases, but the proof by one case is actually enough to deal with all other cases, we use this term without loss of generality. That means even though you are making an additional assumption, this additional assumption does not impact the validity of the proof for all the cases at once. Okay, so how does this go? Well, I want to show that this leads to a contradiction. The fact that is given to me is that mod A minus B can be made less than epsilon no matter what epsilon that is. So I have to choose a special epsilon. I choose epsilon to be B minus A by 2. Okay. Now this is be a positive quantity simply because A is less than B. Now mod B minus A is equal to B minus A because B is greater than A, which is greater than B minus A by 2, which is equal to epsilon, which is a contradiction. This is a contradiction. So, since this case leads to a contradiction, so will the other case, and we are done. So, two elements in an ordered field cannot get closer and closer to each other. Recall that we had interpreted the modulus as the distance to the origin in the case of rational numbers. So, in a similar vein, you can think of modulus of A minus B as the distance between A and B. This just says that the distance between A and B cannot get closer and closer. Okay. This is a course on real analysis, and you have just watched the lecture on the absolute value.